In this lesson, we're going to extend our discussion of trigonometry. We're going to go beyond right angle triangles. We're going to go beyond triangles in general. We're going to be looking at the trigonometry of any angle. So what is that going to look like? We've talked already about something known as the related acute angle. Although if you don't remember that, or if you haven't seen that, I'm going to provide at least a rudimentary explanation of that as I work through this lesson. It turns out that you can draw an angle in any standard position. Again, that's a topic from a previous lesson. You can draw an angle in any standard position, and for any angle, you can come up with what's known as the related acute angle. That's going to be a positive angle less than 90 degrees. If we can come up with that related acute angle, we can draw a corresponding right triangle. And if we can draw a right triangle, then we can come up with most of what we need to know about the trigonometric ratios just in terms of the opposite side, the adjacent side, and the length of the hypotenuse. By applying some principles around right angle triangles and by extending that based on what we're seeing here, so I'm going to make a couple of propositions that hopefully you'll agree seem sensible. Of course, the propositions that I make are actually going to be founded in the actual mathematics. That's going to allow us to do trigonometry for angles greater than 90 degrees, which would be obtuse angles, but actually even for angles greater than 180 degrees. And an angle greater than 180 degrees can't exist inside a triangle. The sum of the angles inside a triangle only adds to 180. So when I talk about the trigonometry of any angle, I really am talking about expanding our treatment of trigonometry to include any possible angle. We're also going to be making quite a bit of use of the idea of the quadrants. When we talk about the Cartesian plane, we break that up into 4 general quadrants. And those are going to tell us about the sign, positive or negative, of the trigonometric ratios. Just to illustrate this with one slide, here's an example. My red line or my red arrow represents what's known as the terminal arm. So in that case, it would be this angle in purple, this angle theta, measured from the positive x-axis to the terminal arm. That is my principal angle. That's the angle I'm actually interested in. You can see that my terminal arm lands in quadrant 2. So technically, this could appear in a triangle. This is an angle between 0 and 180 degrees. Actually, this is an angle between 90 and 180 degrees. I can also figure out what's known as the related acute angle. In this case, that would be the angle between the negative x-axis up to the terminal arm. And these two angles add together to form a straight line. That's the relationship that we use to find the related acute angle there. If I focus on the related acute angle, I can form a nice little acute right triangle. And within that right triangle, I should be able to make use of everything I know so far about sine, cosine, and tangent to come up with some relationships. And then our task, and what will be new for today, is how do I relate that back to the original angle? So let's go ahead and dive in. I'm going to start with something as familiar as possible, which is I'm going to start with a point 4, 3, which has both the x-coordinate and the y-coordinate are positive. That puts it in quadrant 1. So I'm just going to say there is an x value of 4, there is a y value of 3, so that puts my point 4, 3 around there. Let me go ahead and draw in my terminal arm, so that's going to be something that looks like that. The angle that we're going to be interested in, the angle of interest, is going to be measured from the positive x-axis to the terminal arm. So that's going to put my angle of interest theta right there. So that is my angle of interest. And now to make this a little bit more relatable, I'm going to define this, or not define it, I am going to draw this in terms of maybe something a little bit more familiar, which is an acute right triangle. Now, in this case, that comes quite naturally because I can draw one leg of the triangle there. I can draw another leg of the triangle here, and I can even label those. So this one, this triangle is 3 units high. This triangle is 4 units wide. I can come up with the hypotenuse. I'm going to label, if you don't mind, and there's going to be a reason for this as we move forward with this topic. Instead of labeling this h, I'm going to label it r. And so the Pythagorean relationship says that r squared is equal to the sum of the squares of the other two sides. So that's going to be 4 squared plus 3 squared. I've actually chosen my point coordinates, my x and y, so that this actually works out very nicely. I end up with r squared is equal to 25, and r is equal to the square root of 25 is 5. Of course, because r is the length of this side, r is going to be positive. We don't have to take the plus or minus square root. Now, having done that, let's talk about what our different trigonometric ratios are. The sine of theta, with respect to this angle theta, sine of theta is opposite over hypotenuse. And in this case, and let me just go ahead and finish this, this is saying that r is equal to 5. So opposite over hypotenuse is going to be 3 over 5. And something I want to point out to you right away there, something I want you to have in the back of your mind, is that 3 is the y-coordinate, and that 5 is the length of the hypotenuse, which I've labeled as r. The cosine of theta is the adjacent over the hypotenuse, which is 4 over 5. And as before, I want you to keep in mind that 4 was the x-coordinate of our point over the r value. And then finally, the tangent of theta is equal to opposite over adjacent. That's going to be 3 over 4. And that is the y-coordinate over the x-coordinate. And there's nothing more I need to do here because we are working in quadrant 1. All our values are positive. This quite naturally formed just an acute angle all on its own. We didn't have to do anything special with it. Let's move on to quadrant 2. So in this case, I have the point -4, 3. Well, here is an x-coordinate of -4. We have the same y-coordinate we did before, which is +3. There is my point, -4, 3. And just as before, let's go ahead and start with a terminal arm. So there is my terminal arm. I'm not going to repeat the calculation that I did before, but we know that r, because the Pythagorean relationship has me squaring things, well, I know that I'm going to end up with the same value. So we still end up with an r value of 5. This time, to make something familiar, actually before I do that, let me just label. The principal angle is measured from the positive x-axis. So the principal angle is going to be there. And you can see that's an obtuse angle. It's greater than 90 degrees, but it's less than 180 degrees. So let me see if I can express this in terms of an acute right triangle. So what I'm going to do is I'll drop a straight line down from there. That's the height of my triangle. I will draw another line horizontally here. That's the other leg of the triangle. In terms of this triangle, well, that's a right angle. The legs of triangles are dimensions. So that means that even though this is a height of 3, that matches the y-coordinate of 3. The x-coordinate is -4, but the actual length of this side of the triangle is just 4. because we don't talk about a triangle having a side length of -4. And then in between here, maybe I should switch to another color just to make sure it stands out a bit. Here is between the negative x-axis and the terminal arm, that is the related acute angle. So what we're technically finding here, first of all, let's talk in terms of the acute triangle here. The sine of the related acute angle is going to be opposite over hypotenuse. That's 3/5. The cosine of the related acute angle is going to be adjacent over hypotenuse. That's 4/5. And the tangent of the related acute angle is going to be equal to opposite over adjacent. That's 3/4. And these are the exact same ratios that I came up with for theta in my first diagram, which is in quadrant 1. Now we're in quadrant 2. What has changed? And if you take a look at our triangle compared to our values, we'll have an R value of 5, and I'm just going to remind you here that we also have an X value of -4 and a Y value of +3. So in terms of what is the same and what is different, the only thing that has changed here is the X value, the X coordinate of that point. The R value is still the same. The Y coordinate is still the same. It's still +3. So the only thing that has changed is the X. And if you remember from the first page, I pointed out that, well, when we talk about the Y coordinate, that's the opposite side, that got linked up with sine. So we talked about, I said, well, remember, we are working with these relationships, Y over R, X over R, and Y over X. If the X coordinate is the thing that is changed, then that means it stands to reason that the cosine will have changed, and since the tangent also includes the X coordinate, then tangent will have changed. But sine shouldn't change. So if you'll go with me along these lines for now, these are the trigonometric ratios for the related acute angles. That means that, I want to switch back to that other color pen, sorry. That means for the principal angle, we're going to say that the sine of theta is going to stay the same. It's going to be 3/5. The cosine of theta, we're going to reflect that change by the fact that the X coordinate is -4. It's not +4/5. It is -4/5. And the tangent of theta, in this case, is going to be equal to Y over X. That's going to be, instead of just 3/4, that's actually going to be 3 over -4. But we don't normally associate a negative sign with a denominator in our final answer. So I'm going to write that as either -3/4, or you can just write it negative of the entire fraction 3/4. So because of that very small, subtle change in the X coordinate, I actually have changed these trig ratios by quite a bit. What about if we move into another point, -4, -3? Well, now we have the same X coordinate as the previous example, but the Y coordinate is now negative. My point is going to be here, -4, -3. I will draw my terminal arm, just as I did before. I'm sure that many people watching this may be seeing the trend that we're looking for now. If I start to construct a right-angled triangle here, let's do this in order. I don't want to jump around too much. First of all, there's my principal angle. So that's theta. Notice that we are down here. We're in quadrant 3 this time. Then I'm going to, let's see if I can make a right-angled triangle. So I'm going to, once again, I'll use red for my vertical. That matches up with the Y coordinate. I'll use green for the horizontal. And those values, even though the y-coordinate is negative, the length of this side is just 3. It's a side length. Even though the x-coordinate is negative, the length of this side, 4, is a side length. And then we've got this angle between the negative x-axis and the terminal arm. That is our related acute angle. So in terms of this acute right triangle, I could, just as before, I could write that the sine of the RAA is going to be equal to opposite over, I forgot to label the hypotenuse, which is 5. So the sine of the RAA is opposite over hypotenuse, that's 3 over 5. The cos of the RAA is equal to 4 over 5. And the tan of the RAA is equal to opposite over adjacent, 3 over 4. Once again, reminding you that we were interested in this relationship, the y-coordinate over the hypotenuse length, the x-coordinate over the hypotenuse length, and the y-coordinate over the x-coordinate. And just to remind us, what are those values? We have an x value equal to -4, a y value equal to -3, and the r value equal to 5. Now, even though the x's and y's are changing between positive and negative, the r value is staying at 5 the whole time, and that's because we know that r, regardless of where we are here, r was always representing a length. And now I can tell you, as we've traveled around to these points, maybe you can see it or maybe you don't, but I'll give you a bit of a preview as to why do we call this r. And the reason is because what we are describing as we visit these different points is we're actually describing a circle. And the r value actually is referring to the radius of that circle as we travel to these different points. So that's why I chose the value of r as opposed to using h. Now, what has changed? Well, compared to going all the way back to our first quadrant 1 triangle, the things that have changed now, in this case, both our x values have changed to negatives. So I expect a change there, and I expect a change there. My y value has changed to a negative. So I expect a change here, and I expect a change here. Now it looks like all 3 of my trigonometric ratios should be different than those initial values. But we have a little bit of a surprise, and not a good surprise, not like a birthday surprise, but just a result that you might not be expecting. So let's go ahead and say, in that case, what is the sine of theta? Well, the sine of theta should be something like the sine of the RAA. It should be 3 over 5 in size. We just have to figure out whether it's positive or negative. But the y-coordinate has changed to a negative value. So it turns out that sine of theta is equal to -3 over 5. The cosine of theta should have a value that matches the cosine of the RAA. So it should have a value with the size 4 over 5. But the change that's occurred is the x-coordinate has changed to a negative. So it turns out that the cosine of theta is -4 over 5. And remember, these are referring to a theta value in quadrant 3. And here is where the surprise comes in. I hope I didn't build it up too much, because now you're going to be really disappointed. Tan of theta should be something like the tan of the RAA, which is 3/4. But both the x and the y have changed in this case. So those have changed into negatives, but that turns this one into -3, this one into -4, and then we end up back where we started. Surprise. So we end up with 3 over 4. That one didn't actually change. Sine is negative, cos is negative, but it turns out tan is still positive. And then finally, to continue or to finish this little tour around this circle, we have an x-coordinate of 4, a y-coordinate of -3. That puts the point here at 4, -3. I will draw the terminal arm. I know this is maybe becoming a little bit tedious by way of repetition, but I am going to do this for the sake of completeness. I have, let's see, I want to draw in, I'm going to go a little quicker on this one. I'm going to draw, there is my vertical, here is my horizontal, and those two together make up my right angle. So I have a right angle here. I have a length of 5. The vertical has a size of 3. The horizontal has a size of 4. So once again, we have that same triangle. The principal angle is measured from the positive x-axis all the way around to the terminal arm. So there is the angle theta. And then tucked in between the positive x-axis and the terminal arm is the related acute angle. So just as we had before, the sine of the RAA, the sine of the related acute angle, is 3/5. The cosine of the related acute angle is 4/5. The tangent of the related acute angle is 3/4. Let's remind us again, the relationship for sine, that's the y-coordinate over r. Cosine is the x-coordinate over r. And tangent is the y-coordinate over the x-coordinate. Once again, let's talk about what those actual values are. Here we have an x-coordinate of 4, a y-coordinate of -3, and an r value, which is the radius of the circle or the hypotenuse, of 5. Where do we have changes? We have changes, the y-coordinate is the -1 this time. So that means by way of ratios, I expect there to be changes from positive to negative, perhaps, for those two right there. So now if we go to our final statement, the sine of theta, it's going to be like the sine of the RAA. It's going to be 3/5. It's going to be its magnitude. But the y-coordinate has changed to a negative, so it's -3/5. The cosine of theta is going to be 4/5. That's from the RAA. And cosine is x over r. Well, the x is positive and the r is positive, so cosine just stays the same. And then we have the tan of theta, which has to have a magnitude the same as the tan of the RAA. But the y-coordinate here is negative, so we end up with -3/4. And so notice that the only one that was unchanged, and when I say unchanged, I mean unchanged with respect to our quadrant 1 triangle, the only one that was unchanged is cosine. And there's actually a pattern there. When we talk about unchanged, let's instead start talking about positives. In quadrant 1, all of the ratios were positive because all of the sides of the triangle, of course, were positive. The sides of the triangles were always positive, but when we related them to the points, when we related them to the principal angle, it just stayed positive. There was no need to change anything. When we moved to quadrant 2, sine of theta remained positive, but cosine and tangent both turned into negatives. When we moved to quadrant 3, tangent is the one that stayed positive. Sine and cosine turned to negative. And when we moved to quadrant 4, cosine was the one that stayed positive, while sine and tangent were negative. So if we put all of those pieces together, and if you're willing to accept my reasoning that when it comes to how the x and y coordinates are affecting the overall sign, positive or negative, we end up with this pattern. In quadrant 1, sine and cosine and tangent are all positive. And that's where we get the letter A, all. In quadrant 2, only sine is positive, so an S. In quadrant 3, only tan is positive, so a T. And in quadrant 4, only cosine is positive. And the way that we read this, the mnemonic, the memory device that goes along with this is called CAST, C-A-S-T. And you have to remember, when you draw the CAST rule, when you just scribble it out, you always start down there in quadrant 4. This allows us to quickly remember which quadrants give us positive and negative results for the primary trigonometric ratios. So let's put that into practice. And the way I'm going to do that is I'm going to say, well, what are the sine? I hate the fact that we've got the trigonometric SIN, which is the short form for sine, S-I-N-E, and we're also talking about sine plus or minus. So for this, the question then becomes, can I put this into a bit of practice? For the tan of 135 degrees, is this going to be positive or negative? And then I say to verify this using a calculator. Now, I'm not so worried about the verification part with us right now. When I come up with an answer, I'm going to be pretty confident with it. The tan of 135 degrees, well, first we have to figure out where 135 is. 0 degrees is here, 90 degrees is here, 180 is here, and 270. You need to be able to either visualize this or just reproduce it as quickly as I did there. 135 is between 90 and 180. So 135 looks like that. Well, that tells us that we are in quadrant 2. And I'm going to use the cast rule. In quadrant 2, the only thing that is positive is sine, which means that we expect that the tan of 135 is negative. It's going to be less than 0. And if you go ahead and put that into your calculator, and I'll do this one, I'm not going to do every one, but if I take the tangent of 135, I actually end up with a value of -1, which is negative. What about the cosine of 240 degrees? So again, 0 degrees, 180 degrees, 270 degrees. Notice I skipped over 90 because I knew that wasn't helpful to me. 240 degrees is down here in quadrant 3. And cast rule, now you don't have to redraw the cast rule every time, but it's useful because now you can say, well, I'm in quadrant 3. Tangent is positive in quadrant 3, which means that cosine must be negative. The sine of 430 degrees, there's a couple of ways to approach this. The brute force way is just to start counting. So 0 degrees, 90 degrees, 180 degrees, 270 degrees. Well, we still haven't gotten there yet. I add again 360 degrees. Then I add another 90 to 360. That's 450 degrees. And that tells me my angle is here. In quadrant 1, we know that all angles are positive. We don't even need to write out the little cast diagram. So we know that this one must be greater than 0. Another way you could do this, if you don't want to keep circling around your diagram like this, you could just take 430 degrees. And since this is bigger than 360, just subtract 360 degrees from it, or multiples of 360. And in this case, what you end up with is 70 degrees. And of course, 70 degrees is in quadrant 1. So either way is fine. The tan of -30 degrees, now we're used to drawing this with 0 degrees, 90 degrees, 180 degrees, 270 degrees, etc. But that is assuming that we are growing our principal angle in the positive direction, which is counterclockwise. If you are growing in the negative direction, then you have to go clockwise. So this would be -90 degrees. This would be -180 degrees. This would be -270 degrees. Now, I didn't need to go so far as that because -30 degrees is down here. It is in quadrant 4. Cast is the one that's positive in quadrant 4, which means that tan must be negative in quadrant 4. Particularly when you're getting used to these things, when you're just getting started, beware of these negative angles. They can throw you off very quickly and easily. That's why you need to be able to do this blue diagram that I've done multiple times. And you also really should practice what happens if I'm going in the negative direction. Then those are negative angles and they start at the bottom instead of at the top. Okay, finishing up. Now, I say finishing up, I still got quite a bit to do here. I feel like this is turning into a long note, but this is a super important topic. This is the other part that we're going to make use of. So now I'm just declaring this for you. I try to lead you to it. It turns out that the primary trigonometric ratios can be expressed in terms of the coordinates of any point, which are the x and y, and the length of the hypotenuse, which I gave you that little bit of insight. That's actually related to a circle. And so that's why we label it r. So there are alternate definitions for sine, cosine, and tangent, as I've got written here. Sine is the y coordinate over the r value. Cosine is the x coordinate over the r value. Tangent is the y coordinate over the x coordinate. Remember that the r value is determined using the Pythagorean relation, x squared plus y squared equals r squared. So we were talking about this in terms of the Pythagorean theorem, but that is also, and it might be more familiar if I wrote it the way I just said it, x squared plus y squared equals r squared. This is also the equation of a circle. And it's not an accident that those two things look like each other. So that's where the r squared comes from. So let's do one last example that makes use of these principles, and then we'll wrap up this lesson. So let's say I give you that the tangent of theta is -5/24. And then quite often with questions like these, you will have a restriction, which will basically say, these are the values of theta that I want you to consider. I don't want you to consider anything outside of one revolution of the circle. That's the most common one. Where is this theta? Well, let's take a look at this. First of all, let's remember our definition of tan. Tan theta is defined as y over x. So here we have tan theta equals -5/24. Now we could go straight to the cast rule. The cast rule tells us for tangent to be negative, well, we know that tangent is positive in quadrant 1. We know that tangent is positive in quadrant 3. So that means that tangent is negative in quadrants 2 or quadrant 4. So that is our answer. Theta as an angle could be in quadrant 2 or it could be in quadrant 4. Now, another way you could figure this out, the cast rule is just a way to help us remember this, but there is a more pure method to do it. That doesn't mean it's a better way, it's just it makes use of the underlying mathematics. Tan theta is y over x. That means that y over x is equal to -5/24. Now, what could that mean? Well, that could mean that the negative sign goes with the 5, so that would be -5/24. Or it could mean that the negative sign goes with the 24, which is 5/-24. Notice that in the first case, that one is telling us that the y coordinate is 5 and the x coordinate is 24. Well, a positive x and a negative y, that's quadrant 4. Or we could also look and say that the y coordinate is positive 5 and the x coordinate is -24. So depending on how you view that, and both are valid views, this one tells you quadrant 4 and this one tells you quadrant 2. Now I think the cast rule is quicker to do that, but don't think that you must do that. If you already have this information available to you, maybe it's quicker for you to do it this way. Okay, determine the primary trigonometric ratios. Well, to do that, I need to know x, y, and r. So I have to find r using the relationship r squared equals x squared plus y squared. R squared is equal to, well, the x value, it doesn't actually matter whether it's plus or minus 5. X squared is going to be 25, one way or the other. It's going to be positive. The y squared is going to be 24 squared, and 24 squared is, I believe, 576, it is. And so we end up here with r squared equals 601, or r is equal to the square root of 601, because of course r is a positive value. Now that I know the x, y, and r, I can say that the sine of theta is equal to y over r. That means the sine of theta is my y value is either -5 or +5. So that's either -5 over the square root of 601, or, so this is sine theta, or the sine of theta is equal to +5 over the square root of 601. And I could rationalize both of those. Because I'm aware of the amount of time that I'm taking for this particular lesson, I'll just write that out, but I'm not going to go through and rationalize all of them. So long as you understand that that is an option, and that is generally a better communicated answer. The cosine of theta is going to be equal to x over r. And so the cosine of theta is going to be either 24 over the square root of 601, or cosine of theta is going to be -24 over the square root of 601. And notice these things match up with each other. So here we have the, let me see, I will maybe put a box around it. This pair for sine and cosine, these two go together. And this is the pair if we're in quadrant 4. And then down here we have the pair if we are in quadrant 2. I just wrote 4 again. Quadrant 2. So you can see I have one set of ratios for quadrant 4, one set for quadrant 2. I don't need to address tangent because tangent is actually given to me. There's only one ratio for tangent. Tangent of theta is equal to -5 over 24. I'll just write it in its simplified form there. So that was part A and B of this question. Part C is this is going to be the skill that you repeat most often. So although it's at the end, pay particular attention to this. Determine the values of theta to the nearest degree. So solving for the unknown angle is something you're going to do a lot of. And I always write it out as this 3-step process. The first thing we're going to do is calculate what the RAA is. And that goes all the way back to those first slides I was doing, where I was looking at the different ratios. Notice that when I started writing out these ratios in terms of the RAA, I kept using the same ratios, but I always used the positive values of those ratios. Whether the ratios were positive or negative, I didn't care. The RAA always gave me a positive ratio. I'm going to use the exact same idea here. So if the tangent of theta is equal to -5 over 24, that means that the tangent of the RAA is just 5 over 24. So that's the first statement that we can make. Now, we don't even normally write that. Once you get comfortable with this, which hopefully doesn't take you very long, if the tangent of the RAA is 5 over 24, then the way that I find the RAA is I actually take the inverse tangent of 5 over 24. And since there's nothing here to make me think of an exact value, I'm just going to go straight to my calculator for this. The inverse tangent of 5 divided by 24 equals, and I end up with an angle of 11 point, and I'm going to keep 4 decimal places, which is kind of the convention I follow, 7683. 7683, and that's going to be an angle in degrees. So that's step 1. Step 2, we've already done. I'm going to repeat it here just so that I've got the complete solution, because step 2 is to use the cast rule. The original angle theta is, in terms of tangent, it's negative. Where is tangent negative? We've already discussed this. That's quadrant 2 and quadrant 4. And that's all step 2 entails. And now step 3 is to come up with the angle in each of those quadrants. To do this, you need to be able to reliably draw your principal angle. Well, in quadrant 2, my principal angle is going to be here. There's my angle theta from the positive x-axis to the terminal arm. I'm going to have the related acute angle is going to be measured here. Don't forget that this is 180 degrees. The principal angle plus the related acute angle, the two of them together must add up to 180 degrees. So that's the relationship that I'm going to make use of. Theta plus the related acute angle have to add up to 180 degrees. But I'm interested in theta, so the relationship is actually 180 degrees minus the RAA. And so I end up with 180 minus that answer that I gave before is 168. And I'm just going to round this to one decimal, 168.2 degrees. And that is my angle in quadrant 2. In quadrant 4, I'm going to do something very similar. Quadrant 4, the angle looks like this. My principal angle is there. There's theta. That means my RAA is right there. And the relationship between the principal angle and the related acute angle in this case, well, you can see that the principal angle theta plus the related acute angle, that's a full circle. So theta plus the related acute angle is equal to 360 degrees. But we want theta, so we actually rewrite this as 360 degrees minus the RAA. And for this one, we end up with 360 degrees minus, and what was it? Minus 11.8. And so that ends up being 348.2 degrees. I think I've got that right. Yes, I do. So those are my two possible angles for theta. And if I put either of those angles into my calculator, the tangent of either of those angles would be equal to approximately -5/24. And I say approximately because, of course, I could have had, well, I've introduced some rounding error there because these are not precise or exact values. Okay, so that's it for this lesson. I apologize. I know it was longer. There are some assigned questions from our current textbook. This very last slide, I cannot emphasize enough how important this is. This skill, this three-step process, RAA, cast rule, and then breaking it up into the individual quadrants is something that you're going to do time and time again, and you should do time and time again in order to practice this. And that's it for this lesson.